So last time what we defined is, I have to go back quite a bit. So we have defined many things. We have defined these, the notion of continuous functions now algebraically, which is regular function, right? So we defined it via this. I mean, at a point it should be regular, which means that around the open neighborhood U, it should be f equal to g by h, where g and h are coming from the coordinate ring, which is, you can think of it as the polynomial ring. So g and h are just polynomials. Okay, so neighborhood by neighborhood you have to define this, and then we showed actually that in this proof sketch we showed that once you define it locally, it's also true globally. So everywhere it's the same g by h. That's a special property of Zariski topology for affine varieties, for affine or projective varieties. Then based on that we define morphism, which will allow you to compare two different varieties. Right, so this was defined so that it not only takes care of continuity, but it also takes care of regular functions. Right, so for any open set V in Y, phi inverse of V should also be open, and the function should any regular function defined on V should translate back. I mean, there should be a way to pull it back on X or on phi inverse V. Yeah, and then we defined this notion of O. Yeah, so we defined OY, which is the ring of regular functions, and we defined KY, which is the field of rational functions. And it will be strictly bigger than OY. So you should think of OY as the polynomial ring and KY as the function field over the polynomial ring, right? And then we define this for a point also, which is jumps on Y near P. That's O sub Py. Okay, so let's look at these properties quickly. So we have this these three basic properties. So OPY it is obviously a ring. It's a K algebra. It also contains the field K. So it's a K algebra with MP as an ideal. So remember, MP are those germs at P which are 0 at P. They are defined around P, and at P they are 0. Right? They may not be 0 everywhere. So that's an ideal. So one is easy. Second property, you have to show that OPY by MP is mod MP is a field, and this we had shown by simply claiming that, or simply observing that if F is in this, then F inverse is also there, as long as F was not 0.
You have to put the slash the other way around, otherwise it's going to look like a quotient.
What? No. I want to show that OPY mod MP is a field. So take a field, element there, F. It's not 0 means that at P it is not, around P it is defined, and at P it is not 0. So hence 1 over F is also defined in the same quotient ring, right? So this is essentially shows you that OPY mod MP is a field, and which then also implies that MP has to be a maximal ideal. So, all that is implied. Why is it unique? Why can't there be some other maximal ideal also? If you started in a different direction inside OPY, maybe you will get to some MP prime. So, here it is not possible, because what you can show is OPY has only two parts. There is the units, elements which are units, and if you remove the units, then what remains is just MP. Okay, which means that the functions, so the germs around P, either they are vanishing at P or they are invertible. Right, it's easy to see. So either any element is a unit or it is in MP, which means that if you take any element outside MP, then the ideal generated by that will be everything. Okay, so this implies that MP is unique. Basically, all ideals are inside MP. Except the complete one, which is OPY. Right, so this shows the uniqueness of this maximal ideal, and when that happens, then we say that the ring is a local ring. And this is really a definition or term coming from the geometric intuition. Any questions? So, let us prove one more proposition. So, for affine variety Y, and we always assume algebraically closed K, of course. The natural map from AY to OY is a ring isomorphism. I mean, so we have defined this new object O of Y, which is the ring of regular functions defined on the affine variety Y. It will be good if we can realize this algebraically, right? So, I think I probably mentioned this before. We even proved that it will be equal to AY, but let us quickly see the steps of the proof, so that you know that OY is not really a new object, it is only an interpretation. Okay, it is just an interpretation of AY, the coordinate ring, which you can think of as the polynomial ring mod the defining ideal IY. So, the way you prove this is any f in AY so any polynomial defines a function y to k, right, because clearly if f is a polynomial, you can evaluate it at whatever point you want, there is no issue of division by 0. So, that is the function, and which is regular over y. So, this means that we can just think of AY as contained inside OY, right. So, the map phi, the natural map is simply containment, you can think of it explicitly. Now, why is the converse true? Why do not you have anything else, something else other than AY? So conversely, if you take an element in OY, then for every open U, or how did I define it? I think I defined via point. So then for every point and its neighborhood U, or let's do it properly. So for every point in Y, there exists an open U around P such that F is equal to G over H on U for G and H in AY. Okay, so this is the meaning of F, an element in OY. It's a regular function. So any point you pick, there is a neighborhood, open neighborhood, where it is basically a fraction of two polynomials. And then we had this proof sketch that the same G and H you can use everywhere. So this means that F is equal to G by H on the whole Y. Basically, we showed this by taking two different open sets U1 and U2, and then this representation has to match on the intersection. And the intersection is again an open set which is very big. So if the two representations match, if two polynomials are the same on a very big set, then it means they are exactly the same. That was the intuition, and so you get the same representation everywhere, which means what? So this means that 0 of H and Y is, there cannot be any 0 of H, right? So this is empty. But if H has no 0, then it means that by Hilbert's Nullstellensatz, 1 has to be in the ideal H plus IY. Right. So now you come to algebra. So if you look at the ideal which is defining Y and H, that ideal has to have 1, because this is the only obstruction to having a common 0, because we are over an algebraically closed field, right. So 1 is in H plus IY, which actually means that you have equation of this type, G0H plus G1 sum F1 dot dot Fm, where this ideal is, let's say, generated by F1 to Fm. And we know that every ideal has a finite set of generators. So from that we get this equation, and from this equation you get that G0 is H inverse. Mod I. Okay, so H is a unit. H is a unit in OY. So units we denote by star. So H is in OY star. Is that clear? So since H is a unit, so you can just think of G by, so then G by H is basically a polynomial. So G by H is in AY, that's what you reduce. Okay, that finishes the proof. Is that clear? So we have shown that any element of OY is actually in AY, and AY is contained in OY, so you have equality. And formally there is this isomorphism between these two objects. That's an important thing to remember. Um, so that gives you a complete understanding of OY. Now let us look at the germs around a point. What does that mean algebraically? Okay, so now we have to look at this the germs around P. So for this we will need, as I mentioned last time, we will need the idea of localization in algebra, which again is directly motivated from this situation we are in. So what is localization? So for a multiplicatively closed set T of A star, where A is again the polynomial ring and star is removing 0. So maybe I should write here, by this I mean A minus 0. So for a multiplicatively closed set, we define a new ring T inverse times A. Okay, so the ring where elements in T have fractions, have reciprocals. So to make it a ring, we have to introduce everything. So we basically introduce something like A by T, or you can think of it simply as a pair where A is in A and T is in T. And since I want to think of this A comma T pair as the fraction A over T, so I should have defined when two fractions are equal. So I go modulo a relation where A T is the same as A prime T prime if what should happen? A T prime should be equal to A prime T. Okay, so this is the symbolism. By itself it does not make, I mean it is not defined by itself, but the interpretation is that we are looking at these A cross T pairs up to an equivalence relation, and any two of them can be added where the addition formula will be A over T plus A prime over T prime. Okay, so the addition formula for two fractions, so you will get a third fraction, and any two can be multiplied and so on. So it's a ring. Okay, it is forced to be a ring.
For a general ring, that is too strong, right? You just need A T prime minus A prime T being a 0 divisor.
Sorry, what?
So you just subtract one side from the other.
Subtract where?
A T prime minus A prime T. In a general ring, you will only require that should be a 0 divisor.
No, but when A is the polynomial ring, it is fine. And also polynomial ring modulo an ideal.
But that could still have 0 divisor.
No, the ideal will always apply on prime ideals. We'll only use it for varieties. So it's okay, don't make it more complicated. So what Madhavan is worried about is that what if A is a general ring? So in that case the equivalence relation has to be generalized a bit, but let us not worry about that because it won't apply to our case. So is that clear that this is a ring T inverse A? Especially because in our applications we will put 1 in T. Okay, we'll always have 1 in T. So when 1 is in T, then 1 is available in T inverse A. So it's a ring. It has 0, it has 1, and it has for the fractions it has these addition and multiplication rules naturally. So the immediate property is that T inverse A is a ring extension of A. And this is a kind of a unique ring extension or minimal ring extension where all the inverses which you wanted are present. Okay, you wanted to append 1 over t for every 1 over small t for every small t element. So all of them are present here. So this is that smallest ring extension that we have built. Here is the key example. So what happens if you invert everything possible? What is this? So everything except 0 you want to invert, right? Then from polynomial ring you go to the function field, and we call this k small a small k of A. This is called the field of fractions or fraction field of A. Fraction field of A. So for the polynomial ring, k of the polynomial ring is equal to this. Okay, so previously 1 over x1 was not there, now you have 1 over x1, that's the thing you wanted. All the rational functions are there. Another thing we want is take a prime ideal of the polynomial ring A. What can you say about A minus P? So if you take two elements in A minus P, is the product also there? The product has to be there, because if it is not there then it will be in P, but it can't be in P because P is a prime ideal, right? So one of the factors has to be in a prime ideal. So basically this is a multiplicative set. So multiplicatively closed set. So we can actually we can localize by this, we can introduce inverses of this, and that we will give it a special name. So we call A minus P inverse times A, we call this A sub P as the localization of A at P. Okay, so the algebraic operation, it is completely new. I mean, it is basically the instead of including all the fractions to get the fraction field, you only introduce some of them. Okay, so you get kind of infinitely many new objects. So what you do is that you take any prime ideal and then you introduce, you invert everything except prime ideal. Okay, so that is called the localization of A at P. So let us test you. What will happen if you take A to be integers and P to be the prime ideal P? So, what is A localized at P? What is the object? So, you want to invert everything except multiples of the prime P. Let us make it even more specific, the prime 2, right. So, all the odd integers you want to invert, not even ones. So, you get what? You will get numbers like A over B, A, B are integers and B is odd. So, this is called Z2, okay, not to be confused with two-adic integers. This is yeah, it is related but a different object. So, here I mean clearly this is a proper subset of rationals, right. So, instead of going all the way to fractions, you have stopped in the middle, somewhere in the middle, where you only invert odds, not evens. And do you know a special ideal of this ring? So, multiples of 2 here are it's again an ideal, right. This has P times AP as an ideal. So, within this you can focus on multiples of 2. So, basically then you also say that A is even. So, even A divided by odd B, right. So, that's an ideal. And what is AP mod PAP? So, if I call that ideal again P, AP mod PAP is no. So, then so what was A mod P? That was just the finite field with 2 elements. So, you get the same thing here. You get the Galois field F2, just 0 1. Okay. So, you can do the same thing, but now it is kind of buffed up to this infinite object, which is very different. It is basically these fractions, and you can yeah, it's a way to embed the finite field in different kind of fractional rings. And yeah, so we have defined till now this localization and localization by T and by a prime ideal. The same thing we can do also for projective case, where you have to take care of homogeneity. So, what will you say is T inverse? Now we call it S, right, because S was the graded polynomial ring, where we only look at where we look at the homogeneous parts of your polynomial. So, this here again you want to look at fractions, but then you want to use the grading. So, you will say that the numerator and denominator has the same degree, that is an extra condition. So, you look at S comma T pairs, again thinking of this as S by T, such that S is in S, T is in T, and so these have to be homogeneous. Are homogeneous of the same degree. and modulo this understanding that two fractions are equal if this cross product is the same, right. Is that clear? So, it is just a modification to the homogeneous condition, and similarly we can define for a homogeneous prime ideal P or I of S, we have the localization Si, right, which is a special case of the thing above. Right. So, now we have some good properties, or in fact we now have good objects. Using this A sub P, the localization, we can now understand the germs at P. So, what you can show is that for affine variety Y, for all the points in that variety, OPY is the same object, the same ring as the coordinate ring. So, well, clearly it is not the full coordinate ring, it is a subring of that, which are defined in a neighborhood of P, right. And sorry, it is not. Yeah, it's an extension. So, let me write that and then explain. So, OPY is clearly a subset of KY, right, because KY are the rational functions which are defined on Y somewhere. In particular, if you look at those rational functions which are defined around P, then you will get OPY. But algebraically we have identified which ones are those. So, these are the ones which come from fractions G by H, where G comma H is in AY in the coordinate ring, and all you need to be careful about is that H should not be in MP, right. H should not be a germ which is vanishing at the point P, because then G by H will be undefined. Yeah, so with that care you have identified what OPY is, and with localization. So, this is the localization of AY at the prime MP. Is that clear? Remember that MP is a maximal ideal, so it is clearly a prime ideal. Okay, so we are localizing AY at this specific prime ideal, which happens to be in fact maximal, and that is what OPY is. So, what happens if you localize AY at the prime ideal 0? What is this? So, if you invert everything except 0, then you should get the maximum, which is KY, big KY. Okay. So, only at 0, localizing at 0, you will get all the rational functions defined on Y. For everything else, you will get a proper subset, which is this ring.
Why is it called localization?
Sorry?
Why is it called localization?
Oh, because of the picture. These are the functions which are defined only around P in arbitrarily small neighborhood. So, the global, I mean functions that are defined everywhere globally are ay, and if you only want to look at those functions which are defined in an extreme vicinity of P, that's ay sub MP. So localization is the precise exact term that you want. That's exactly what the definition of OPY was. And it also follows by our earlier results that the geometric dimension that we define for a subset of the affine n space, in particular here for the affine variety y. So that dimension is equal to transcendence degree of ay and also transcendence degree of this field ky, big ky. Okay, so all these three things are the same, because when you localize you don't increase the dimension, though you don't increase the transcendence degree. So ay sub 0 has the same transcendence degree as ky. So from that you can see the three things are equal. Any questions? Okay, so yeah, let's see a quick example. So in the affine plane, let's look at the affine variety x2 square minus x3 minus x1 cube. So what is the function field of this big ky? What are the functions maximum possible which are defined somewhere on y? We don't care about everywhere, but somewhere. So this will be, you can unfold the definition and just check that it's actually this. Okay, so look at the rational functions over k in x1 variable, and then so that's a field, and over that field you basically are introducing square root of x1 is the same thing. So this is the same as in x1 you are introducing square root of x1. Is that clear? You are actually introducing x1 to the 3 by 2, but which is the same as x1 to the half that you are introducing. Okay, so that is the set of maximum, the biggest set of functions which are defined somewhere. Note that there are many things here which are not defined everywhere, right? Even if you look at 1 over x1, it's not defined everywhere. For example, it's undefined at 0, 0. But that doesn't stop us from calling it a function of y, because at least it is defined in a large chunk which is an open set. So most of y these things are defined, but somewhere there are these undefined zones. And so let's look at that. So the point is 0, 0 in y. What are the functions defined at that place? So what is OPY? Right, so OPY is the coordinate ring localized at MP. Okay, what is MP now? So MP is this ideal x1 comma x2, right? It's the ideal which should be maximal, so it should actually correspond to a point. The point is 0 comma 0. So the ideal can only be x1 comma x2, right? It sets both the variables to 0, and clearly that is a point on y. So that's the ideal, and you just have to look at the fractions by the definition. So this will come out to be K, the polynomial ring modulo this ideal, and then you localize it at the ideal x1 comma x2. Okay. So it looks complicated, but I mean slowly if you unfold that definition, it won't be so complicated. You should just think of the thing inside the bracket to be just polynomials in x1 and x2, and you are allowed those polynomials to be divided by polynomials which are not in x1 comma x2 ideal. So they should not be constant free. The denominator should not be constant free. That's all it is saying. So for example, it has this object has 1 over 1 plus x1 plus x2, but it does not have x1 over x2, right? Because the problem with 1 over x2 or x1 over x2 is that the denominator x2 is in the ideal. So that clearly geometrically also you can see that it's something which is undefined at the point P, while the first function is defined. Is that clear? Similarly, 1 over x1 minus x2 is also not defined, and here 1 over 1 plus x1 square is defined, and so on. So you get a good idea of, you get a complete understanding of what these functions are, you can explicitly work with them. Okay. So what we will do now is we'll think of this O as a functor which is taking you from geometry to algebra, right? You are going from these the affine n space to the function field. So we'll call it OX acting on something. Then this functor we will use and generalize this. You can think of this OX as the functor of ordinary functions. Okay, you can think of O as standing for ordinary functions over X in a neighborhood. So that dot will be, for example, you can, if you apply it on the whole of your affine variety, then what you will recover is what we have defined before, OX. Or you can look at it on a open set. So these will be regular functions defined on U. On open U. Okay, so we'll think of O as something more general instead of just the ring object that we have defined. We'll think of this as a functor. It's taking something from geometry and landing in a very different area, which is algebra. And then if you take a limit of these open neighborhoods around the point P, then you will get the germs. So it takes a point which is in X to OXP. Okay, these are the germs. Is that clear? So, I am changing the notation a bit here. I am changing it to OX dot. So, you can apply OX on a, either you can apply it on everything, or you can apply it on a open subset, or you can apply it on a point. Okay, these are the basically two kinds of applications. So, this functor is key in algebraic geometry. So, it takes you from geometry to algebra. And there is a fancy property it has, which is that it is contravariant. So, contravariant means that it reverses the morphisms. So, for example, if you have a morphism from some affine variety X to affine variety Y, then what can you say about OX on, so say there is a, say we first apply it on the whole thing. So, what can you say about OXX and OYY? So, when the arrow goes from X to Y, then after applying OX the arrow will be reversed. Okay, so, the arrow will go from here to here. So, in geometry basically if you are trying to cover Y by X, then in algebra you are going to a ring extension of OYY. Okay, so, covers are like ring extensions. So, covers correspond to any questions? So, this we had seen also happening when we defined morphism, but now it is more precise in terms of this OX functor. So, we will frequently be reversing the arrows and doing the analysis in proofs, right. So, if you defined OXU, okay, so then look, let us look at an example of OXU for an open set. Let us consider a special open set. So, this will be called a distinguished open set. For a variety X and an element of the coordinate ring X sub f. You want to define X sub f. So, the distinguished open set XF is defined as follows. So, it is basically the set of those points in X at which f will not vanish. It is as simple as that. So, this is the points on the variety at which Fp is non-zero. Okay, so that part of the variety X, it's clearly open, because in Zariski topology we have defined open as complement of closed. So the closed subset will be f of I mean those points P such that f of P is equal to 0, and this is the complement of that. So this is the same as X minus Z of f, right. So that's closed, this is open. This is called a distinguished open set, because if you understand these open sets, then you understand all other kinds of open sets. Okay, these are the only open sets you need to study. So why is that? Any open U is a union of distinguished ones. So what is the proof of that? So U is open, which means that it's complement of some zero set, right. So U defines a J such that this happens, and you also know that any ideal J has finitely many generators. So we write it as F1 dot dot Fm. So any open set is basically just a complement of the zero set of some roots of polynomial system. And so another way to write this is, see, the zero set is an intersection, so the complement is a union. So you write it like that. So it is the union of X minus ZFI, which is union of X sub Fi. Is that clear? Because complement means that one of the Fi's will be non-zero, right. So any point in the complement will be available in some ZFI complement for some I. So in other words, open sets are union of finitely many distinguished ones. So distinguished open sets you should think of as giving you a basis. It's of course an infinite basis, but any open set you have in mind can be represented by using finitely many of these. Okay. So this contains a lot of structure from algebra. So these they actually form a base. Of open sets. Okay, so instead of basis we call it a base, right. So I have defined this just to test you on what is the O functor on this XF. Can you give me that? What is O X functor on this open set XF, this distinguished open set? So what are the regular functions that are defined on this part, which is the part of which are the points of X that don't vanish, don't annihilate the polynomial F? It's very simple, right. The functions G by H, all you want is H should not be divisible by F, right, basically. So we will show that it is actually this. It is the multiplicative set generated by F, and then you make these things invertible. Okay, so you introduce, so all the functions which are defined everywhere on X was Ax, and when you are looking at this neighborhood Xf, then or this open set Xf, then you are also allowed to invert by powers of f essentially. So you can divide by f, you can divide by f square, f cube. These will also be defined on Xf because the denominator doesn't vanish, and we'll call this, we'll denote this by Ax sub f. Okay, that's the proposition and the definition. Is that clear? So let me write it maybe that f is just powers okay. So by bracket f I mean the multiplicative closed set generated by this single element, so you get only powers. What is the proof of this? Well, so what we just defined, clearly Ax sub f, anything here is defined, I mean it is regular on Xf, right, because g over f or g over f square, these things are defined on Xf. So that part is clear. We have to show the converse, that's the non-trivial part. So conversely you take let us say phi in O in this, and we have to show that this phi is just like g over f to the r. So let us look at the possible denominators, this h that I am talking about. So these h such that h times phi is in Ax. Okay, so let us consider all these possible denominators h such that h times phi is a polynomial in the coordinate ring. And what we have to show is that these h are essentially coming from bracket f. It's like f to the r, right? Nothing else. Okay. So first thing you observe is that J is an ideal. Is that clear? Because any outside element of Ax, if you multiply it with h, then then h phi continues to be in Ax, right? So it's clearly an ideal. And yeah, I think another thing which will be useful to remember is that X has the following decomposition. Because any point in X, either it annihilates F or it doesn't, right? So there is a clear coverage. These two things cover X. The question you have to ask is whether these two components are disjoint or can there be a common point. So let's analyze that. Let P be a point in Xf. Oh, and okay, this J is also connected here. Let me write that. If P is in XF, then oh, this is trivial, sorry, this is trivially disjoint. Because if Fp is not 0, then clearly P cannot be Z of F. So, this is by definition. So, this is a disjoint union, covers X. The question that you have to ask is if I take a point P which does not annihilate F, then there exists an H in that ideal J says that H at P is non-zero. Is that clear? That's just from the definition, I think. Because the phi, yeah, so here you are using the fact that phi is regular over xf, right. So, phi over xf already has, I mean at the point P, it has a representation like G by H, and if you use that particular H, it happens to be in J, and it clearly would not vanish at P. So, this just follows from since this phi is equal to G over H on a neighborhood containing P. Okay. So, for any point P in XF, there is a polynomial in J, in the ideal J, which is not annihilated by that point. This is just parsing through the definition through the hypothesis. Which means that the point is not in Z of J, which means that XF and Z of J are disjoint. Is that clear? So, any point P that you pick, for any P, you will find an H at which is such that H at P is non-zero, and so that means that basically XF cannot have a common point with Z of J. And when that happens, then you should invoke Hilbert's Nullstellensatz. So, is that what I want? Sorry, okay, there is one more conclusion. So, now you look at the orange note. So, since Z of J is disjoint with XF, you deduce what? It is a subset of Z of F. Yeah, and on this you can apply the ideal functor. So, I of Zj is then, it then contains I of Zf, which will give you what? So, by Hilbert's Nullstellensatz, you get that radical of J contains F, which means that there exists an R such that F to the R is in J. Is that clear? And yeah, that is also, J was the collection of all possible denominators, and we have shown that F to the R is 1. This means that phi is equal to some G over F to the R, which is an element in AXF. That is what you wanted to show. Is that clear? So, it is a simple argument, but you have to get familiar with how to keep switching between points and rings and ideals. So, but you have learnt ultimately a basic geometric fact that the functions which are defined on points which do not annihilate f, their denominator is a power of f. That is all. That is what you learn, and of course, this is our algebraically closed field that we are always assuming. Okay, what else? I think the stock, the germs thing I have done, right? Yeah, OPY we have studied. So, fine. Yeah, so now we have a good handle on the OX functor. We understand what it is, how does it act on the distinguished open sets. So, OX of XF is just localization by this powers of f, and we understand how it acts on everything. So, OX of x is just A of x, and finally how it acts on a point, that also we understand. So, OX comma P is the localization of Ax by MP. Yeah, so that gives a complete understanding of the OX functor. Fine, I think yeah, this is all done. Correspondingly, yeah, so analogously you can define for the projective case also. So, for the projective case, for a projective variety x, the regular functions defined on x of f, the definition of x of f will be similar. Like these are the points of the projective variety x which do not annihilate f, the polynomial f. So, this will be what? So, analogously you can show that this will be the homogeneous functions, I mean homogeneous g over f to the r, where degree of g and degree of f to the r is the same. So, this is basically the set of those g over f to the r such that g and f are in some SD, sorry, no, not the same SD, g f are homogeneous in S, and degree of g is equal to degree of f to the r. And r is a natural number. Okay, is that clear? Yeah, so that would be the definition of Sx localized at powers of f. You always have to take numerator and denominator equal degree, and then again you will have to say this again, OX functor will be clear. What is OX of x? So, this we had argued before, right, that this will be the only thing that remains that works everywhere is constants, right. OX of x is just constants, and finally the germs, what was that? So, for projective variety x containing a point P, what is OXP? So, this again is like before, Sx localized at MP, right. So, MP is the maximal ideal that defines the point P, and you just localize by that. It is also a prime ideal of S. So, that will be the same thing. Okay, so there is a nice thing that is happening here. So, this OX functor, if you look at it on the whole of X, then it seems that all information is lost, because only the functions which are the only functions which now remain are the constant ones, right. So, then it is not giving you any information about the projective variety X itself. While if you look at the germs, that has perfect information. As you go over different points, you will get different parts of Sx localized. So, what you should learn from these two results is that though OXX, so OX functor is trivialized at X, for a projective variety X. The local information at point P is perfectly preserved. Okay, so which is why these functors, so you, if you look at it globally, then it will have fewer information, but if you look at it locally, which is especially around a point, it will have all the information which you will want. Okay, so we'll also use this philosophy often. The local information is the true information. So, next time we will next we define a more local kind of morphism. We have already defined a morphism. Next time we will define what is called a rational map. So, we can write it maybe to make the arrow different, rational on top. So, we will define how to compare x to y in a more local sense without asking for definition everywhere. Okay.